Thanks, Lawrence. Thanks everyone for coming. We're really going to tangle with entanglement now because, like you say, there's so many subtleties in what I'm going to talk about. People have been asking me, am I finally going to understand entanglement? Well, I don't even understand entanglement. So we're just going to go through this learning process together, I guess. And like Lars mentioned, we just finished, or we're just finishing now, this large program here at KITP called Entanglement and Strongly Correlated Quantum Matter. And what I really want to get across today is why this program was really exciting for me personally, and I think for a lot of the participants. And one thing that I'd also like to get across is like how unique KITP is in terms of bringing all of us here together to talk about these types of ideas. So the thing with entanglement is really a language, a common language that we can all use in different fields of physics, sort of to talk about what we're interested in. And by fields, I mean, things like I've illustrated here, I guess, which make no sense. But this is supposed to be gravity. It's supposed to represent many of the participants who work in gravity. Field theory, some abstract equation. Quantum information, which I'll talk about. In my field, condensed matter, which I learned here as a graduate student. And so I know you look at this and you're like, okay, it's just a congregation of a bunch of nerds. Really, how is this exciting? Or how is this different than anything else? But really, one of the points to get across is that, imagine the way we sort of approach physics. I mean, a lot of us choose our career paths, maybe even in our early 20s. 22, 23, we choose either to study the geometry of Einstein's equations, black holes and stuff like that. I study low temperature materials. You take I don't know what that is, Jello or something, and you cool it down to almost absolute zero, and it has all these amazing properties. Very, very different, right? Quantum information people, when they started studying the field, which really only kind of exploded in the 90s, this is a very mathematical field. A lot of mathematicians were in the field studying the idea that you have these quantum building blocks of information devices, like your next iPhone or your next computer or something like that. And the field theorists, many of these guys came from high energy. They were interested in how very high energy particles, like what you see in these super colliders, the Large Hadron Colliders, what's the fundamental quantum mechanics that govern the interactions that you see there? That's quantum field theory. And really what we did is we came together here, and over the last 3 months, Lars locked us in a room, basically, and made us get along, right? Like we basically found a common ground, and I'm going to tell you about some of the things that maybe they're a little abstract, but they're really exciting. And I want to also get across the point that they can lead to future technologies and very interesting sort of future applications that aren't that far away. So, but before we can have any of that fun in this talk, we have to talk about what is entanglement. Like, what am I talking about, right? And you'll hear many different perspectives on entanglement. But I'm going to build up the idea of entanglement from a perspective that's very sort of microscopic and what I'm used to thinking about in my field. And that's the idea that very delicate bonds can form between microscopic, maybe atoms or particles, when they're isolated quantum mechanically. So I want you to start by thinking of a particle. And this is my electron. Okay, so I always think of them as blue. I don't know why. It's impossible. Essentially, an electron is a fundamental lepton. It's a point particle. I mean, there is no sphere, really. I mean, it's just a thing that exists in our most fundamental theories. And it has certain properties. Mass has a mass. It has a charge. The charge is the thing that makes everything here work, right? It's like what electronics is based on. It also got, electrons occupy different positions in space. And they have different velocities and momentum. All these things are properties of the electron. But the one that I'm really interested in is this thing that I drew here, which is like an arrow, which is supposed to represent something we call spin. And you can think of spin as just another property of an electron that you're just not familiar with dealing with. It doesn't give you any. It doesn't give you an iPhone. It doesn't give you any useful or interesting current applications to sort of generalize. But there's something very special about spin in electrons, and that's that you can manipulate the states. You can change the spin. Unlike Unlike charges, charge is fixed. The mass is fixed. I don't know what the numbers are, but people know the numbers for these things. And I thought I'd give you a flavor of how us physicists talk about these things that we're interested in by writing a few equations. And even though they might look unfamiliar to you, I hope the point will get across in some sense. And one way to sort of distill down the idea of spin in an electron is to just write a mathematical equation for what the electron is. And like I say, we never really think of it as a blue ball. We think of it as some abstract thing called a wave function. And the wave function is the reality of the electron. And it's sort of an imprecise mathematical reality. I mean, we don't really know exactly what the wave function is. We write psi. We think we're so clever because it's Greek and it looks complicated, right? But this is a real equation. I write this on the chalkboard all the time. It's psi equals some funny brackets for some reason, and I'm saying this is the state of the blue electron. Its spin is pointing upwards. You can imagine it's amazing how much fundamental physics comes out of crazy-looking equations like that. But what we're trying to say when we write this is that we're boiling down this very complicated quantum mechanical wave function, which again we have a very sort of imprecise knowledge of, into just a few ingredients, just maybe one ingredient that I'm actually interested in for my current application. And right now, that's the so-called spin of the electron. Incidentally, it's called spin because you can imagine this blue ball just spinning here. And this would be like the direction of the axis of rotation, I guess. Just like the Earth is a north and south pole. It's not really like that. Like I said, there's no blue ball spinning in space. But the point is that this object that I kind of write mathematically has the same properties as an angular momentum. And so it's called spin because that's something that's familiar to us from sort of our everyday life. The idea of angular momentum and so on. And the challenge with quantum mechanics is that a lot of the concepts, which have a classical analog, are sort of like subtly different in a way that can trick you. And there's even concepts that have no classical analog at all. And that's really what entanglement is. So that's what I'm getting to here. So to think about a little bit more about what entanglement is, imagine I had two electrons. And this one I decided I want to be red for some reason. Just to distinguish these two objects. But really, again, what I'm interested in is the spin of the electron. And maybe they have the same charge, maybe they have a different charge, maybe it's electron, positron. I'm kind of glossing over all these details just to say that I have another spin state here in the object right beside my first electron. And I can look smart with another funny looking bracket here. I can just say the wave function of this object is a spin up for this electron and a spin down for this electron. It's really just labeling somehow these spin states. Amazing. Done. We're done. That's all the math. No, just kidding. That's awesome. The weird thing about entanglement is I just told you that spin was a property of the electron. But I can create an object out of those two electrons that the overall object, the two electron object, has a definite spin, maybe 0, 1, something like that. But knowing that doesn't give me enough knowledge, enough information to discern the individual spins. And that's what entanglement is. It's like the whole doesn't give you information about the parts or something like that. Okay? And here's how I would draw it as a cartoon. I have two electrons, again, red and blue. And now, instead of arrows, I'm just saying, okay, I got some purple bond here. And what that purple thing is telling me is that there's some spin state of this whole object. And again, think of isolated electrons. Maybe they're trapped in some way in a very delicate experiment, or maybe they're floating around in free space somehow. But if these things are created in just the right way, maybe an electron-positron that pops in and out of the vacuum, like a vacuum fluctuation they call it. Or maybe if you have just the right type of electronic excitation in a crystal or something, these two electrons can come out with a purple bond, whatever that means. And it means that these two things don't have, individually don't have that property of spin that I just claimed that every electron has. But they have some configuration of spin that's shared between the two of them. And really they're one object in and of themselves. And the way I would write that equation would be like this. So here's my wave function. Okay. And remember last time I said I just had a definite spin up and a spin down for red and blue. But if these things are created such that they're entangled, I actually have two different possibilities, let's call it. I could have the arrow up here and the arrow down here. Or I could have the opposite, the arrow down in blue and the arrow up in blue. And that's one of the simplest ways, even though it looks fancy with all these brackets and stuff. I'm just really labeling the states of these two red and blue objects. And of course you can't draw it with the classical description because there's no way of saying, this object that I've created, this vacuum fluctuation or something like that, is equally well described as up-down as it is as down-up. And that's entanglement. In a nutshell, the idea that this object has no definite individual spin description, but has an overall property that I call purple bond. That's the idea of entanglement. And the thing you might have heard about entanglement before is that this sort of non-trivial correlation between these two quantum objects has a consequence for how they interact with each other. And that is the idea that in order to discern between this possibility and this possibility, I have to make a measurement, what they call a measurement on this state. And a measurement can be as simple as a thermal fluctuation that jiggles one of these things in such a way that it has to choose up or down, say. Or it can be something as artificial as me creating the situation in a laboratory where I literally put a magnetic field on that constrains or measures the spin of this or the spin of this. Okay? And so, for example, one way that I could look at the individual spin states of this electron system that bubbled out of nothingness would be to measure whether or not this is spin up and spin down. And again, like I said from this equation, you can see there's two possibilities. If this one's measured as spin up, then the red one, which I'll presume I don't measure, has to be spin down, and vice versa. And so in some way, when I make this measurement on the blue, that's what we call maybe collapse the wave function into just this object that I looked at before, one that has a definite spin up and a definite spin down on blue and red, which is no longer entangled. And that 1 over root 2 out front that looked fancy, that was just a way of saying the probability of this was equal to the probability of the opposite spin state happening. So in that sense, I've taken an entangled object and I've measured, if you will, the blue or the red, either or, and it's determined the state of the other one, the one that I haven't measured, through this wave function. And that makes sense, Makes sense when I had this PowerPoint flashy thing happening. I can totally see how that would happen. But it's actually fundamentally the weirdest thing if you kind of take this to its logical conclusion, because it violates this notion that these two particles have to actually physically interact with each other in order to maybe exchange information or in order to influence each other's states, for example. So I've drawn a space and time axis here, and I've taken two particles, or two electrons, that I've brought rather close together, but not close enough that they actually can see each other. There's no signals going between these things. I'm ignoring any electric fields and so on. If they're completely isolated like this, there's no way for them to actually influence each other unless I drag them to a different position at a later time where they actually maybe hit each other, or they're close enough to look at each other's quantum state, or whatever this influence is that I'm talking about. And this is the idea of locality or causality. Actually, who was in Ted Jacobson's talk about a month ago? Remember this talk on General Relativity and so on? So for those of you, for you experts in causality, the reason that I drew this diagram like this is because Ted showed these cones. It's called the light cone. And in the initial position of those two electrons, this is the region of causal influence, they call it. So this is, again, space, as Ted would draw it, and the vertical here is time. It's a cone just because my space is in 2 dimensions. And this edge of the cone represents the speed of light. And so if this electron moved at the speed of light, it would actually move along this path here. It's space-time, and so the slope gives you the speed of light and so on, the constant c. And what I did on the last slide was I started these two electrons some distance apart. And again, they can't causally influence each other by any signal because nothing goes faster than this line here. Nothing goes faster than the speed of light. So in order to make them see each other, if you will, or influence each other, I move them up to this little region where the causal cones, intersect. So at some later time, these two particles go up and they can exchange states or something like that. But the weird thing about entanglement is this thing I told you before, where I've created these things out of the vacuum. I've created this pair of particles, and they have this purple thing linking them. I don't know what I did there. I got so excited I jiggled my thing. So my purple bond that links them can be broken by this measurement. Say I measure blue, and it'll instantaneously, that was supposed to be instantaneous, whatever that means, influence the state of the other one, right? So the thing we call the wave function collapse, if you will, happens despite the fact that the blue and the red were separated such that no possible signal in Einstein's theory could possibly be transferred between these two things. And that's what's fundamentally weird about this wave function that I wrote down that seems so simple. It was just up, down, plus down, up. But it implies this. If you take this through its logical conclusion or endpoint, it implies the fact that this influence between the particles happens despite these causal cones, despite this idea that Einstein gave us.
Regardless of distance.
Regardless of distance. You drag it to the edge of the universe. It's a strange, it's why it's weird, right? So it's just like we're used to this idea of locality. I can only influence things by touching them or speaking, and there's a velocity for my voice, and then I have a laser pointer that the photons have the velocity equal to the velocity of light. And all this causal influence is what Einstein built into his theories. And we're very used to thinking about this. Locality is just the statement that you basically have to be in this region of causal influence in order to have influence. And entanglement fundamentally violates that. And just by the nature of that equation, it fundamentally violates that constraint. And we call it a non-local correlation because it violates this locality. And Einstein hated that, right? I mean, this is all happening in the 20s and 30s. And Einstein had this great triumph. This idea of relativity and special relativity and general relativity and so many amazing things were happening. And then along came these quantum mechanics guys. It's like, again, it's the 20s and 30s. And they were working on something that was equally as fascinating, but so different than what we're used to intuitively thinking of, that even Einstein didn't like it. It even boggled his mind somehow. And this is everyone's favorite quote from Einstein. He called that sort of non-causal or that non-local link spooky action at a distance. It seems so unsophisticated when you compare it to what Schrödinger said. Schrödinger was basically one of the fathers of quantum mechanics. He's like, listen, Einstein. Yeah. I wouldn't call that, entanglement. Okay, number one, it's the characteristic trait of my theory, right? But entanglement is the thing that forces you to think about the universe different. It's the very thing that you can't get an intuition for. It just is the difference between quantum mechanics and classical mechanics.
How can we prove empirically that it's correct?
Good question.
That it occurs instantaneously if we can only measure things to the speed of light?
Great question. So people ask this question a lot during this time. And 30s and 40s. I mean, it's fascinating. It's pre-war when all this stuff was happening. And the theories that happened in the 20s and 30s, they still influence all of our lives daily through. And there's very little technology, sort of like experimental, or there's no digital computers and so on. So after the war, I guess in the 50s, might have been the 60s, I forget exactly, people finally resolved this idea. So this debate went on for 20 years. How do we know that this is right? How do we know that there's entangled things? Maybe there's little, where did let me go back here. Maybe there's actually a little arrow up there and a little arrow down there. And I don't know how to measure it, right? I mean, we just fundamentally, we didn't have radar back then, right? Like technology was fundamentally limited. And so it was very plausible that people just didn't have the technology, I guess, or the way of thinking, that would show us that this is insane, right? This whole idea that you break this bond and it moves, the influence moves despite the speed of light is completely insane. So after the war, Bell, actually, I think it was actually 50 years ago, actually maybe it was a bit more recent, 50 years ago this year, that this gentleman Bell said, okay, he gave a firm set of mathematical relationships that could be experimentally tested to show this idea. Okay, it's called Bell's inequality. I didn't actually put it in my talk because I don't quite understand it. But I understand the consequences. So what Bell said was, if you do an experiment where you entangle things, and these experiments today are routine. I'm going to say routine because my friend does them up in Waterloo in his laboratory, so I see them every day. But if you do an experiment where you entangle two things and then you measure the correlation, and so the way these experiments are done is a laser is shot into what's called a nonlinear crystal. And there's this process called parametric down conversion where you produce two entangled photons. It's not electrons, it's photons. So two laser beams come out essentially. And each photon in these laser beams, it has been prepared in such a way that it has the equivalent of up-down. It's actually a polarization state. It's like a left or a right moving polarization state of just like when you have polarized sunglasses. You can have circularly polarized light. And it's created in this entangled pair. And so what these people do is they separate these entangled pairs at a distance such that when they hit a detector and they look at the correlation, oh, here's one coming in, this one's right, this one's left. Or here's another one coming in, this one's left, this one's right. There's no possible way that a light-like signal could have traversed that distance. So they actually separate these things physically far enough that when they detect these photons coming in, there could have been no possible signal between those photons, for example.
But couldn't the entanglement have happened at the moment of separation? So at the moment they separate, one goes down, the other one is forced to be up, and they remain that way.
Right, but you can also create them so that they're not separate. They're not necessarily at the same point in space when they become entangled. So, although I've kind of simplified the picture, you can create entangled objects that can be separated by a distance, or are created while separated at a distance. But anyway, so these types of experiments basically prove what this mathematical relationship is, Bell's inequality, which I don't have in my talk, but I encourage you guys to look up. And the experiments were done in the late 70s. So it wasn't really until the 70s that people really understood that, even though it looks like a quirk in some sense, we can show this in the laboratory. This entanglement, this way that we view entanglement is absolutely real. And what it requires then is, like Schrodinger said, a departure from classical thought. It's just a real phenomenon that smart people have figured out is experimentally testable.
And the measurement itself doesn't change the result?
The measurement
the
does.
Observation, the viewing?
Yeah, the viewing. So these things, I didn't draw. My picture isn't that accurate. But these things remain entangled until they're measured. So typically they'll measure one, and then look to see if the other one has the proper. They'll measure up, and they say, "Oh, that one has to be down." We measured this one as being down. That one has to be up. And they can physically separate these things, and then collect all the data and bring it together at a later time. And say, "Yep, sure enough, there's these certain types of correlations."
So in this measurement, the simultaneity of the measurement is shorter than the time of flight between the two detectors.
The simultaneity of the measurement is shorter than the speed of light between the two detectors. Yeah, they call it closing loopholes in this argument, and it's a very active field actually. A lot of people think of all possible loopholes. It's very fundamental, right? So people are interested. Some people separate these things physically. Some people put the photons through different fiber optic cables and wind them up on the floor in these big stacks. So the photons actually going kilometers in these fiber optic cables before they're measured and before the entanglement's seen. So there's all sorts of crazy things. So my friend at Waterloo, he takes his students and he puts them in this little trailer out in some cornfield in the middle of winter. And some of these grad students are manning one of the detectors while he's warm and safe with like the other detector in his lab. That's how these things are done. Grad student abuse. So you're right to be skeptical. Number one, because I didn't explain it well. But number two, it's really like I said, the thing that departs from classical thought. So at some point, you just come to peace with the fact that you don't understand it like me, and then you move on, using it as a building block for all of your theories. And I'm not alone in this. Actually, many people have moved on from this fact that it seems bizarre in some sense, and they've taken and moved the field of entanglement into something that can actually produce technology. And by studying entanglement, people, very smart people, starting basically from the early 1990s, came up with a lot of ways that entanglement, instead of just being a curiosity that is the reality of some microscopic world that we never see or experience, it's actually something that can be a resource for technology for future work, future applications. And this resource-based view of entanglement is what sort of formed the modern field of what we call quantum information. Just like classical information is the underlying theory of how your computer works, quantum information is the underlying theory of how some technologies that might seem bizarre are actually coming to light and very close to commercial application. So one of them, which is interesting, is called ultra-dense coding, which is just a funny word, but you know how you're always so disappointed in your iPhone or your computer because it's so slow. Things you download, it's always bandwidth limited. Well, quantum information scientists knew a long time ago that if you could take, your modem or your router and your computer, and you could combine, the physical channel, maybe the Wi-Fi or the Ethernet or something that you communicate between these things, with entanglement, then you could actually condense the information in a way that's impossible classically. It's called ultra-dense coding. So you can take your bandwidth and actually exponentially increase it with entanglement.
So the implication is that there's no distance limitation if you could measure it across that distance.
Even better, there's no distance.
Yeah.
The idea of distance wasn't in my equation, right? There was no x or y or anything in that equation. Literally, there's no distance at all in entanglement. It's non-local. It doesn't care about your regular.
That's just weird.
It's awesome. I heard awesome. That's what I agree. No, it's true. It's what these technologies are based on, is the idea that there's non-locality. There's not really an idea of space and time in the same way in quantum mechanics. But literally, people can use this for what they call ultra-dense coding. Or quantum cryptography is a big one. So the idea that you have entangled maybe senders and receivers, and you can have perfect encryption that no one can spy on. It's absolutely perfect. No man in the middle can listen and hear what you're saying. I mean, in a non-technical sense.
So the NSA would be out of business.
Hey, they might be listening. I don't know exactly how my computer works. And quantum computing, speaking of the NSA, I'll get into this a bit, but quantum computing is the other big application. And the field of quantum computing is very real, and it's expanding rapidly all the time. And everyone wants a quantum computer. Everyone wants all these things. Your computer that is infinitely faster in terms of its communication, is perfectly secure, and what the quantum computer promises to do is actually break encryption, the classical encryption that we use in all of our communication technology since the time of Turing himself, essentially, since the time of the U-boats and all that. All the basic foundational theories that our encryption is based on can be cracked by a computer that uses entanglement as a resource. And everyone wants one of these things. Microsoft has a huge quantum computing effort right here, right across the courtyard in Ellings Hall, called Station Q. And that's only part of Microsoft's, actually. They have a huge quantum computing group also in Redmond up in Seattle. IBM out in New York. They don't, it's not just like they're building Watson 2.0 or whatever that. They want the quantum Watson, right? And Google made a huge foray into quantum computing just recently when they took John Martinez, who is a faculty here in physics, and essentially bought him or purchased him in order to make a quantum computer for Google. I mean, it's real stuff, right? And
they have an office here too, don't they? Google has an office.
Google has an office in Galita, I think. I don't know if it's here on campus, but maybe someone can tell me. But they're very interested in this idea. And again, if you don't believe me, because I sound paranoid, the Economist a week ago came out with this amazing article about quantum computers attracting commercial interest. And they talk about some of these efforts that I talked about, which are very, two of these at least are centered on Santa Barbara. They're coming out of Santa Barbara. It's amazing. And so here's the race. Here's the quantum computing race. We don't know when these cars are even going to start. But, people. This David Simmons did this to me. Superconductors. So the best candidates for certain types of quantum computers are superconductors. They're superconducting qubits, they call them. And that's what John Martinez and also IBM is working on. Photonics. This is there's like a son of photons in there. This is one of the oldest ideas behind quantum computing because it exploits like the same idea with this laser and this parametric down conversion and entanglement, which is a kind of an old technology in this field. Trapped ions. That's another leading candidate. These are very sort of academic. These happen in universities. Some of these private industries that I talked about, are pursuing some of these ideas. But the best, just like you said, is the NSA wants this, and they really want this. And in Snowden's documents, he released basically the evidence that the NSA is pursuing a quantum computer. It's fascinating. They want a quantum computer to essentially break not just current communications, like they don't want to listen to me Skype, hopefully. But they can go back, once they have a quantum computer, they can go back and decrypt all the communications back until World War II. All the diplomatic cables and everything all the way back, from the beginning of time. Because presumably they've stored all of this information and they're just waiting to crack it. So this is the Economist here. It's just like, you don't know what exactly they're doing. Nobody knows what they're doing exactly because they keep it secret. But they're definitely working on some aspect of quantum computing. So I guess the question is, who do you want to hold the quantum computer first? Anyway, I digress. I got a little paranoid. Why do I like entanglement? I'm not interested in world domination per se, right? I like entanglement because I get to come to KITP, and like I say, Lars locks us all together in this room, and amazing things come out of the combination of our fields. And so for the remainder of the talk, I'm just going to give you a flavor of how us regular academics, who aren't building quantum computers necessarily, use entanglement in our research and more accurately kind of use it as a way of communicating with each other. Any questions on anything up till now?
Are there any serious challenges to this idea that are still not been beaten down or that are still respected?
The challenges are so serious that if you asked me to put my money on quantum computing, I probably wouldn't.
Okay, that's the good answer.
That being said, I don't have much money. So.
Yeah.
The Canadian dollar is quite low right now. But like a smarter man than me said in the courtyard, the amazing thing is that the most brilliant people in the world are working on quantum computing now. So, the most brilliant people in the world also worked on the atom bomb. And it was a very short period from its inception to its being built. And what a lot of people see now is, in order to build a quantum computer, you have to essentially industrialize a lot of this idea of quantum information. It's almost not enough to try to do it in an academic setting in terms of money. And that's why essentially Google wants to industrialize the process. Just in the same way it took the industrialization of America essentially to build the atomic bomb. So it's a similar challenge.
There's a little difference there, though. The atomic bomb, there was a pretty good confidence. It already made atomic piles in 1930. Whatever. There was, I think that around the world, in Germany, and there was a feeling that if you could bring together that much uranium, you pretty much have something.
Correct.
But
and the difference here is you don't know if it'll ever work.
Well, that's my point. It's from the very beginning. And your illustrations, honestly speaking, I find unconvincing because they're based on the concept that we create things together when they're in close proximity.
You mean these
separate them?
Oh, the entanglement. Yeah.
Right, so you're kind of, it was a little bit of hand waving there, if you don't mind my saying so.
No, it's
In that, and when they're created, they're within the same light cone. And then you jump to a later state in which it kind of illustrates your point. But it doesn't, it really skips over the interesting part. There you go, that's the perfect example.
Yeah.
I mean, there's nothing special about creating the two particles simultaneously in different spins. You just let them separate and then you say, oh, now we got something. It's
Right.
just not convincing to me.
So that's okay. I mean, again,
I mean,
not
I
very
don't wanna
convincing to
give you a
me
hard
either. But that is solid. The idea of non-locality entanglement is absolutely solid in the scientific community. What's not known about the quantum computer is whether or not you can isolate the electron to a sufficient degree to keep that entanglement alive long enough to do what you want to do with it.
So
'Cause
it's
maybe
more
it's just-
analogous to an engineering problem as opposed to a basic science.
That's
A little bit.
a little bit. I mean, people think they have very firm ideas for quantum computing. For example, John Martinez, and for him it's an engineering challenge. He would tell you it's an engineering challenge.
In this diagram, where you have entangled particles, if you were able to change the spin of one of them,
That's what this does. This
instantly
changes.
change this.
It changes the spin of this one.
Yes, this one would change. The
Yeah,
opposite.
But
exactly.
you can't
Because
know
the
that.
total was 0 before.
You can know that. I just can't explain it. No, it's absolutely, yeah.
And isn't it true we already have quantum computers? It's just a few bits.
Sure, definitely, yeah.
So it is an engineering challenge to
Right, so John
this one.
Martinez unveiled a 9-qubit, essentially, building block for a quantum computer, maybe in March or April this year. And it was in, you could look this, you can look up 9-qubit quantum computer, and you'll see, basically right out of UCSB, this construction that he made. It's based on the superconducting quantum qubits idea of it. So in that sense, it's just an engineering challenge. But like I say, what's not known is whether or not you can keep things isolated enough that this very delicate purple bond that I drew isn't sort of broken by maybe thermal fluctuations or some other thing that's inherent. So that's why I don't put my money on them. Not because I don't believe in entanglement. It's because it's not clear that you can sort of you can isolate it in such a sense that you can use it for these things. I should say that entanglement's not the only ingredient in a quantum computer. It's also superposition, which I'm not talking about in this talk, but I alluded to here. And that's the idea that if you take a single quantum spin of the electron, and that thing's not being observed, you prepare that electron somehow, you create it, then that electron spin can exist in what they call a superposition of maybe up, down, sideways, all sorts of directions. And it only chooses its state when you measure it. So there's another ingredient in a quantum computer that also is a very weird thing of quantum mechanics that's not entanglement. So it's actually these two things that have to go together. You're right to be skeptical. It's a very important topic. So
Being skeptical.
yeah.
Because when you have that superposition, and you go back to your simple experiment, and you measure one of the elements over here, the other has the same combination of X, Y, and Z, but in the opposite direction.
Right. So you can only actually do the measurement along one axis. So you have to choose.
So
Okay.
it's a probability of what you get along that axis.
Right. Right, and you could actually rotate that axis and try to do a measurement in the other axis too. And then, depending on how you prepare the state, if it's entangled, you can get the opposite outcome for the second particle and so on. So there's an arbitrary choice there.
How do you know you don't have some kind of a wormhole looking at the same electron in a mirror image?
That's a good question. Literally never thought of that before. Maybe that's what happens. I don't know.
Can momentum of two particles be entangled?
Yes. Yep.
Wow.
So if you have, in my favorite system here, you have a very cold, say, crystal of electrons or atoms or some other object, and those things can have different momentum states. They can move collectively in waves of momentum. You can actually entanglement between all these different momentum states. And if you measure one momentum state, it'll affect another momentum state in the crystal. In momentum space, not in real space. So it has nothing to do with space in some sense. And that's, again, what's counterintuitive with the whole thing.
It seems like entanglement is an accepted that everybody believes in it and has for a really long time.
Absolutely.
Why wasn't I taught about it when I was
Why wasn't I informed?
and it's in graduate school? I mean, was it not considered important, or was it considered too dubious?
I think it's because of this, people maybe are thinking about it more. That maybe people didn't think there was a practical application. And I say it wasn't until the 90s that...
It wasn't in engineering school.
Well, it wasn't until the 90s that this sort of, the idea that you can use it as a resource came out. It was really in the 90s that people started saying, okay, it's not just this crazy way of thinking about locality or something. It's literally something that we can build things that are demonstratable in the lab, to exist only because of entanglement.
But it was also in the 60s that Bell came up with his stuff, and then the 70s when
they did
said,
the measurement.
Oh, yeah. He's right.
Yeah, totally. Yeah, so okay, I forgot the date. Bell was the 60s. That laser thing was the 70s. This was the 90s.
I was there in the 60s.
I wasn't there till the 70s. So. Okay, all right, okay. Why do I like it, man? Who cares if it's weird? I love it. It brings us all closer together, especially literally in this room. So in order to develop a common language, we'll do something fun here with entanglement. We'll quantify it with something called an entropy. And this handsome gentleman is Claude Shannon, who is the father of classical information theory. In some sense, Claude is really interested in the fundamental mathematics behind how your radios work, or your communication devices work, or how you transfer digital information across channels, or how your computer works. He's the father of what we call classical information theory. And he came up with something called an entropy, which you might have heard about in a physical system before. But he came up with an idea of applying this to information. And why is it information? It's like if I'm talking in that one cup and you're listening in that other cup, and you can somehow quantify the noise in that channel, then you can also quantify how much information is lost by this noisy connection. Or if I compress my data down and then transfer it, how much information have I lost? And is that information loss, is it critical to the understanding, to the uncertainty of what's going on or not? And that the basics of information theory can now be applied through this entropy, which I'm going to talk about, to entanglement, my favorite thing. The single particle that's entangled, or the pair of particles that's entangled with this wave function, and even more complicated things. The things that are the building blocks of the quantum computers, or these other devices that I talked about, which are many electrons together, maybe in a material cooled to very low temperature, that has all sorts of crazy entanglement. I don't even know what's red and what's blue anymore. Everything's green. All these crazy bonds of entanglement that can exist in reality, and have some crazy wave function that has multiple spins. There's many of these funny brackets describing every single possible electron in this thing. All of this complicated ideas of entanglement that exist in real materials at low temperature can be quantified through this entropy of Shannon's. And how do we do that? Well, if you were here last time, Ted Jacobson had a demonstration with Apple, so I had to bring a demonstration. I brought a loonie, because it's Canada Day, by the way. Happy Canada Day. We celebrate the fact that we, don't need to be independent to be happy. I don't know what it is. So let me take that entropy formula and apply it to the dubious object that's a coin, a Canadian coin perhaps, that can have two heads or two tails, or anything in between. Okay? Some magical coin. And if you have a coin that's a regular coin, you do something like this, there's a 50% chance that lands heads, or as we call them, queensies, or tails, I guess it's called loons, I don't know. It's 50-50. But if I had a double-tailed coin, every time I flip that thing, there's no uncertainty in that measurement. There's no uncertainty into the outcome. It's always tails. And if I had double heads, if I had heads on both sides, same thing, there's no uncertainty in the outcome of that measurement. Okay? You do this, it's always heads. And so I've just written the probabilities that go in this equation. So this thing here is a sum over states of the coin. There's only two of them. It's heads and tails. And if I label the probability of heads with this variable x, which I'm varying from 0 to 1, And the probability of tails is just 1 minus the opposite, 1 minus x, because probabilities always have to add to 1. Something has to happen when I flip that coin. Then I encourage you to do this calculation. There's 2 elements to this sum. It's 0 log 0, or 1 log 1, for each one of these options. Or if you went in the middle here, the regular coin, it would be 1/2 log 1/2 for the heads, and plus 1/2 log 1/2 for the tails. And I won't write it, because I don't have that much time. But that would result in a log 2. And you get this curve of uncertainty. It's 0 when you're completely certain, and it's log 2 when you're completely uncertain, or maximally uncertain, I guess. And entanglement can also be quantified in this way through entanglement entropy. And if I put on the origin of the plot here, my favorite up and down electronic state, and at 1 here, say, the down-up state, and I did this calculation varying the amount of entanglement, where at the top it's maximal. It's my up-down plus down-up. It's my fully entangled state. I would get the same curve as the coin, essentially. And what I've done here is I've quantified the uncertainty that if I have, say, one of these starting wave functions, and I do a measurement, but I don't look at it, whether or not it's definitely going to be up-down, definitely going to be down-up, or something that's one or the other. Okay, so I didn't explain that very well, but it quantifies the uncertainty in this dubious process that happens when you measure one of these things and you don't know the outcome yet. And so entropy quantifies uncertainty, and it tells you something about the information that you have. It's telling you something about the information that you have about the red if you measure the blue and vice versa. Okay? And what I want to do is take this idea that I can quantify the uncertainty involved in this entanglement and apply it to much larger systems, something where I can't exactly calculate that curve. And what I'm interested in is these many electron systems at very low temperatures. Very low temperatures, so things that we essentially look at in a laboratory. And then I started to ask myself, well, how do I take this 2-spin idea and extend it to many spins? And is it useful somehow? Well, it depends on the state of matter. And I mean, I'm a condensed matter physicist. We came from a rich history of semiconductors, and then correlated systems, and then there's breakthroughs in our field of superconductivity and so on. Very practical things, which are made up of many electrons and many spins. And we're used to classifying our states of matter. Maybe at high temperature, you could have states that are thermally excited, and things move around. And usually what happens when you have thermal excitations is you break up all that entanglement. If I went to low temperature, even 0 temperature, I may get different states of matter that don't have entanglement, but break something called a symmetry. Maybe all my spins are up and down in a pattern like this. That's called a symmetry. And that symmetry dictates the properties of all sorts of materials. And the theory of my field of condensed matter has, up until a few years ago, very definitely been based on this idea of symmetries. But since I've been boggling your mind with entanglement, you might ask, what happens if I had a state like this? Which could happen, by the way. If I had a 0 temperature state that doesn't seem to break symmetries in the actual maybe charges or spin components, that breaks symmetries in the entanglement structure. Or even worse, or crazier, or better, what happens if the entanglement structure has no symmetry? And it just sort of bonds everywhere, and there's entanglement in a way that we don't even know. By the way, these things exist. And we have theories that describe these materials, and we can create them in a laboratory. So back to this idea of entanglement entropy. What I was doing with the coin was I was quantifying the uncertainty of the measurement. And for the entangled state, I measured the blue particle, and it told me something about the red particle. But here there's many particles. So what I have to do is I have to extend my definition of entropy to include a red region and a blue region, which I didn't color because I ran out of time. So this red region, I could ask, how is that red region entangled with the rest of the particle? And I can draw this circle. And if you look at this circle long enough, like I do, And they pay me to do this. It's amazing. You'll see that if you just said, okay, well, the entanglement of this object is just, the entanglement between the red and the outside can just be quantified by counting all these bonds that cross this boundary. Here's one, I don't know. I'm too far away. 2, 3. Maybe there's 3 or 4 of these things. I can say, okay, there's 4 of these things, maybe 4 times log 2. I can almost figure this out. And you might say, okay, the center of this thing, this region that I'm interested in, doesn't have any bonds or entanglement, if you want to call it that goes outside of the region. So it doesn't share anything with the outside. There's no connection between the outside. And so really what this tells you is that the entropy, which is just counting all of these purple things, scales as the size of that region there. And if I make that region bigger, I'll only get more entanglement entropy proportional to the length of that boundary, because everything entirely inside or entirely outside is unentangled with the other region. And I just wrote one of the most fundamental equations that we deal with every day in this program for the last 3 months. It's called the boundary law for entanglement entropy. It was so simple when I did it here, but it's one of the most fundamental things that dictates sort of how we think about entanglement. And even if I had this crazy state where many bonds are inside and they're long and they're connected to the electrons outside, if you want to think of it like that, what you find if you actually do these calculations, and believe me, I do them all the time, and the way I do them is I simulate the quantum crystal on a classical computer with all the laws of quantum mechanics, and then I measure the entanglement entropy between this red region and everything outside of it. I also find that the entropy scales as L. So instead of a log 2, you get this really, really weird idea that in all materials and theories that are real, that we know exist in our universe, we get this very fundamental scaling for the entanglement entropy. Oh, wow, that was weird. Even this state of entanglement, which is, I don't know how to draw it, but it's the state of matter where the entanglement has no scale at all. It doesn't even know the atoms are there. And you can create these. You can tune a crystal at a very low temperature, so it sits at a very fine-tuned point in the magnetic field, such that the entanglement spread out across the entire thing, the macroscopic object, is completely entangled in and of itself. They call it a critical point or a phase transition. And at these phase transitions, again, if you do the calculation in very laborious ways like I do them on the computer, you'll find the area law, the boundary law for this entanglement. The entanglement entropy scales as the boundary. And this is almost an empirical fact that we discovered over the last several years. And actually, again, this is a Santa Barbara connection. Mark Strzenicki was one of the first people, who's a faculty at UCSB, to identify that this scaling law applied in quantum field theories. So actually, literally, this thing came out of Santa Barbara. And I love this thing because this scaling law, this fundamental law of many particle entanglement entropies, is really the language that connects all of us together. Like I mentioned, I do essentially numerical studies where I build a virtual quantum crystal in huge supercomputers, and I measure directly the entanglement between all of these particles as they evolve with the equations governing quantum mechanics in time. Like Mark Strzenicki, who first developed this, actually works in a very mathematical realm of quantum field theory, the fundamental theories of high energy physics, which is very different. But he came up with the idea, essentially, and also the gravity people now routinely use this boundary law, which they call holography. It's like a holographic a compression of all your information onto that boundary in their gravity theories. And let me just tell you what the gravity people told me in the last few days, the last few months. And I don't understand it, but it's really fun. So they say, look at that purple cloud. You're simulating this thing on a computer, and you're basically contributing to global warming, the amount of waste heat that's coming off your CPUs. But I can show you how to do this in a different way. They're like, I got rid of the purple cloud. I don't know, it's causing me problems. So just imagine I have entanglement in some material, like a real material in a laboratory. You can literally build these things. And I want to know the entanglement entropy, the amount of uncertainty I have of a certain part of the crystal with another part that I can measure. Maybe you can only measure the surface or something like that. So they said, take your region of interest, which is two-dimensional here because I can't do three dimensions very well. So imagine it's two-dimensional. Flip it on its side. So I flip this thing on its side. And now that's a two-dimensional plane that my circle sits in. And actually, I'll just draw the plane here, okay? This is just a two-dimensional piece of paper that I'm interested in only the entanglement entropy of the red with the gray. Oh, I drew gray instead of blue, but you know what I mean. The gravity people would come to me, and they did, and they said, instead of simulating that thing directly, you can essentially embed that in a higher dimensional space. And that higher dimensional space, which is now 3 dimensions, and it's hard to draw, has a curvature from general relativity that comes from the solutions to Einstein's equations with a negative cosmological constant. This thing that determines whether or not the universe is expanding or contracting. So if you take the equations from the contracting case, and you embed this thing in this higher dimensional gravity, then what happens is if you take this red boundary and drag it out, because it's negative, because it's negatively curved, it'll actually curve in on itself and form a surface. And the surface area of that surface, over 4, for some reason, I never understood, times Newton's constant, which is fascinating that it's in this equation, gives you exactly the thing that you're trying to calculate using all those CPUs. And it's absolutely true. And it's just a fascinating connection between these guys who think in terms of metrics and curvature, and it's completely classical, you know, and it relates to my system of jiggling electrons that has this purple cloud. It's like it's finally taken Einstein and Schrodinger and made them kiss or something. Let me think of it in another way. What is this negative curvature thing? What am I talking about? Right? It seems crazy. Let me just reduce everything down one level. I'm almost done. Don't worry. And let me think of a wire. And in that wire, I have a bunch of entangled electrons. And I'm interested again, just like Claude Shannon was, in the uncertainty of information contained in that channel or that wire. But I'm interested in a quantum mechanical sense. So I have entanglement. I have a perfect purple cloud inside of that wire somehow. And I define a region, a boundary, with sort of 2 boundaries, define a region. And say I can do a measurement on that part of the wire. But what's the uncertainty or what's the entanglement entropy that governs what I know about the gray part of the wire? So the gravity people said to me, okay, well, one thing, make your wire infinite. So don't worry about the, all right, okay. You know, it seems crazy. This is how they think. Make it infinite and then make it connect to itself, even though it's infinite. So basically make a circle, okay? And if your wire is big enough, it's effectively infinite. And now I want to know what's the entanglement entropy, again, of this region and this region, where this is like my boundary. This is the thing I was calling L, but it's now lower dimensional. So what this gravity space is, they call it anti-de Sitter space, this negatively curved solution to Einstein's equation with a negative cosmological constant. What it's equivalent to is putting a lattice of space points, or space-time points, inside of that circle. And the person who captured this best was this guy, M.C. Escher. Remember this guy? He drew all these crazy pictures of staircases and stuff. And he also drew all these negatively curved spaces, which perfectly describe basically the so-called negatively curved or hyperbolic or anti-de Sitter space that the gravity people, I actually took this from some person's gravity talk. People are talking about gravity theories. They use this. And the idea is that the white spines on the fish, from nose to tail, are 1 unit of length. So this fish is the same size as this fish, is the same size as this fish all the way down, just like turtles, right? Right, Kevin? And as you go out to the edge here, there's an infinite amount of fish. Oh, it's like a Canadian's dream, an infinite amount of fish. and it's actually, the distance from the center fish to the edge fish is infinite. And that's the description of this Einstein space-time. And what they said to me is, if you know the points of your boundary, and you draw the geodesic, or the distance between these 2 points, the minimal distance, it's like on a sphere, there's a geodesic that corresponds to maybe great circles or something. Here it's a different type of geodesic, which looks like that. That's the shortest distance between those 2 points in this space-time. That's exactly the quantum mechanical entanglement entropy of that one-dimensional wire of electrons. And they can calculate it with a very simple formula that I don't show here. But it's like a fascinating... And, okay, it's getting weird. It gets even weirder. If you warm that wire up a bit from absolute zero, because everything I've been talking about is like very cold. You just put a little bit of thermal excitations in there. What they told me is this puts a black hole in the center of your space, and that geodesic has to avoid the black hole. And the warmer you get, the bigger that black hole gets, until it pushes the geodesic out into this sort of infinite region here and makes your entanglement infinite, essentially. And it seems absolutely crazy, but I can take my virtual crystal on the computer and warm it up and do this measurement and confirm exactly what the gravity people say. And even though there's no fundamental, I don't know, maybe Esha knew it. People don't know the deep connection between this. There is a deep connection. And that's basically what we've been exploring here at KITP, is this very deep connection. And these gravity calculations and all these field theory calculations and what we do on the computer, it connects these things like that we're interested in, takes this fundamental law of Mark Schernicki's from UCSB and allows us to calculate very delicate subleading terms to this scaling law that are absolutely universal. They're the same in gravity, they're the same in different materials, they're the same in all sorts of physical systems. And it's kind of like the insight into what's deeper, what's below this thing. And if that's too esoteric for you, actually, this idea of entanglement entropy and these subleading corrections that can be calculated by these methods give us some fundamental corrections which identify, maybe in this state of matter, what we call topological phases even. So this is what's going on in Microsoft Station Q right now. This is my one slide that explains this. Is that they have a highly entangled set of states, electronic states, which through entanglement entropy, which you can calculate with all these different theories, identifies these as being topological. And what topological means is I wrap this thing into a torus, there's a degree of freedom associated with like a flux through that torus that is the quantum bit of the quantum computer. And that thing's fundamentally stable against decoherence, against little thermal jiggling, because if I screw up a little piece here or a little piece here, it doesn't affect that abstract topological bit that goes through the center of that torus. And that's exactly what these guys are working on at Station Q. And it comes from, very deeply, this connection between all these different fields and entanglement entropies. And that's it. That's all I want to say. Entanglement's fascinating. It'll be the technological building blocks of the quantum computer. It gets me together with gravity people, and it's fun. And I have high hopes. I think it's real, and we're going to build new materials based on this in the future. And thanks so much for your attention, guys. It's been fun.
I want to ask a question about deep connections, and probably help me if you go back to the slide that showed the negative cosmological constant calculation. Keep going. That one. Okay, good. So, if I understood correctly, you're saying that you could calculate this entanglement entropy using a gravitational calculation, and the constants that you're putting in are from Einstein.
So the equation that describes this bulk space is Einstein's equations of gravity, classical gravity. Yeah.
Okay.
So there's a space here, essentially, that's like a GR space, the General Relativity.
Okay, and so, fundamentally I want to ask, well, what the heck does that mean? But maybe more specifically is like, where do the properties of the electrons, et cetera, come into doing this calculation? How does that G number down there know anything about electrons?
It's a very deep question. So, what connects electrons to materials, or to theories of quantum field theory, to gravity? It's this idea that in certain states of matter, say, if I prepare the electrons in a certain way, they'll display what's called universal behavior. And it has to do with the fact that, essentially, you get rid of the notion of space in the equations that describe the electrons. So the electrons have quantum equations of motion. And if you prepare the electrons in a certain way, those equations collapse down to something that's very, very simple, and is also used to describe other things in physics. And I don't just mean other states of matter, I mean other field theories and so on. And I mean, this is a very hand-waving thing, but this is essentially connected to what David Gross did for his Nobel Prize, is some of these ideas of universality, they call it. The idea that there's universal connections that are very fundamental between all of these theories. And it's a little hard to understand. I mean, I'm obviously not explaining it well. Maybe someone can do it better, but there's just universal properties that connect these things together, but only if you tune the electrons to certain very special states of matter. I don't know. But once you know you have universality, you can throw the electrons away and do the gravity calculation.
If momentum could be entangled, how about mass? Have they ever tried seeing if the mass could be entangled between two?
Good question. Mass is usually a property that's fixed, I guess. So you always somehow know the mass of particles. So
I think in neutrinos, actually.
Oh, good answer.
Neutrinos are mass eigenstates, right?
That's an amazing answer, right.
What was it?
Neutrino physics is an example of that.
Oh, great. So they come from the sun entangled? Is that right? I don't know. I don't know anything.
Electron neutrino.
The oscillation?
Yes.
Yeah?
It's electron not mass.
I learned something.
I was just curious, with entanglement, distance isn't important.
Mm-hmm.
Just wondered, we know with relativity,
Mm-hmm.
within a space-time, world,
Mm-hmm.
but I don't know that much about quantum mechanics, but are there other situations where there's just no agreement, or where space is irrelevant in quantum mechanics, as in quantum entanglement?
I think it's the most striking example of where you don't need to know. Yeah, space wasn't in my equations. Yeah.
Right.
So typically, if you want to know something about an electron, you have to know the full wave function, which again we don't precisely know what it is. Would have a spatial component that would tell you if it's in this room, for example, maybe a momentum component, in addition to the spin component. And you can't get rid of that. I mean, the electron has to exist somewhere in space. So it's only when you boil things down to something at a bit more abstract level, where you throw away the idea that the electron's in this room and you really just concentrate on the spin states, that you really don't need that notion of space. But in general, I mean, I could think of examples where we don't use space in our equations, but I think it's somehow fairly fundamental in all other aspects of quantum mechanics.
Is every particle entangled with another one? Do they change who they're entangled with? Are particles and antiparticles entangled with each other? How do we know who's entangled with whom?
Good question. Good question. So, yeah, in general, you wouldn't imagine that everything's not necessarily entangled with everything else, because maybe there would be consequences that we don't observe on a day-to-day life. But we can definitely create entanglement. And you can do it with this particle-antiparticle idea. So if you create an electron-positron, they'll be entangled. But you can also put particles near each other or have an interaction. Maybe electrons that are near each other but interact via their charge, their Coulomb interaction. And if you let them just naturally follow that evolution dictated by the quantum mechanics equations of motion, they'll naturally get entangled together. So if you isolate them, put them together so they see each other, even if they start unentangled, they will entangle themselves at a later time. Then if you measure one of them, you'll break that entanglement bond, and it all starts over again. Yeah.
All right, well, let's thank Roger.